Okay, we continue with our study of transducers. Uh, we were learning about transducer characteristics. We learned about the static characteristics, right? Um, then we started learning about dynamic characteristics. So the dynamic characteristics, we got the um, let me go from the simpler ones: settling time or response time, then slew rate, then frequency response, then impulse response, right? uh, Now we started learning about modeling of transducer. The transducer has two parts. One is the mechanical side, the other one is the electrical side. So we have the physical input. It could be acceleration, right? So we want to measure acceleration, then we use what is known as the acceleration transducer, and the output is electrical, right? So we have the electrical uh, part of the transducer. So if I want to model, I can model mechanical separately, electrical separately, but that would be a problem when you want to analyze it. So one way of uh, dealing with this is we have an equivalent electrical uh, for the mechanical parameters. Then what I can do is I can transfer all mechanical things to electrical, and I can just use one electrical model which would represent both the mechanical side and the electrical side of the transducer. Okay, and in that we saw that in the mechanical side uh, we have the classic equation m d square x by dt square plus d dx by dt plus ks into x is applied force for the mechanical side. And on the electrical side, if I have a RLC circuit or series, L series, C series, then I have L series into d square q by dt square plus R into d q by dt plus 1 by Cs Rs into q equal to uh, the total voltage. This is voltage across the inductance, voltage across the resistance, voltage across the capacitor. So total voltage in the circuit. This is E, right? It is also possible that I can have uh, the CRL circuit. So I have E here. Uh, then we have C, I call it C parallel, R parallel, L parallel. So C parallel into d square phi by dt square plus 1 by R parallel into d phi by dt plus 1 by L parallel into phi equal to I, right? So now we see that these two are This is called the direct equivalent, direct mechanical to electrical equivalent. This is called the inverse mechanical to electrical equivalent. Let us look at the direct equivalent. In the direct equivalent, which we already saw, if I compare these two, right, what I am going to get is displacement x is charge q, right? So this is displacement x is equal to charge q, right? Then we have force equal to electromotive force, mechanical force is EMF. Mass behaves like an inductance. The damping, it could be viscous damping, it could be frictional damping, doesn't matter, is resistance. And the spring elasticity becomes 1 by capacitance, right? So we can look at the two equivalent and we can use either one of them. It depends upon the particular type of equivalency that we want to look at, right? Okay. Okay. Now, once I have the differential equations, the easiest way to understand and operate a given set of differential equations is to use the Laplace transform, right? So, what is a Laplace transform? If I have x of t as my signal, which is in the time domain, right? Then I transform it to the Laplace domain with an x variable s is integral 0 to infinity x of t into e power minus st dt. This you have done in your control system, you have done in your mathematics. So I'll go through it very quickly. Here s is called the Laplace variable. And we have s is equal to sigma plus j omega. We call this as a complex frequency, and the way that we look at it is, if I look at e power minus st, right, which is equal to e power minus of sigma plus j omega, which is e power minus sigma into e power j omega, right? And if I look at this, this is, if sigma is positive, then it would be e power minus sigma would be something like this, exponentially decreasing 1 if sigma is positive. Sigma is negative, of course it will be increasing 1, and j omega would be sin omega t plus j cos omega t. So it's a oscillatory function. So this is actually the Laplace variable. Okay. So we have done the Laplace variable, right? We already know that the Laplace transform of del of t equal to 1. Fourier transform of del of t is also 1. And the way that we look at is, I can you can go through it. Laplace transform of u of t is 1 by s, right, and so on, right? So if I have these values, I can definitely uh, convert my time domain quantity into uh, frequency domain quantity. And once I have the frequency domain quantity, I can actually get back my time domain quantity. So I can now say x of t is Laplace inverse of x of s, which is given by 1 by 2 pi j uh, into limit t tending to infinity, uh, t tending to infinity, integral k minus jt to k plus jt into x of s into e power st ds. Okay, it's we will not be doing all this mathematics, right? We will be only applying this to analyze our sensors. So if I have a, mechanical side, we already know m d square x by dt square plus d dx by dt plus ks into x is the force, right? So if I now apply Laplace transform, I get m into s square into x of s plus d into s into x of s plus ks into x of s equal to f of s, right? Or I can rewrite this as x of s into ms square plus ds plus ks equal to f of s, right? Then I can easily calculate the if I have the mass, damping, all those values, I can actually put this equation and calculate whatever I want to calculate. But what is uh, happens is, if I take this to the right hand side and bring this to the left hand side, then x of s divided by f of s is 1 by ms square plus ds plus k, k ks, right? K suffix s for the spring. Okay, so we call this as the x is the displacement of the mass when I apply a force F. So F is the input, and uh, displacement is the output for the mechanical system. In that case, then this is output by input in the Laplace domain. We call this as a transfer function. Of course, it's not enough that I look only at the mechanical side. I also have to look at the electrical side. So it may be that I have the function like this in the mechanical side and one more function in the electrical side. I can combine both and write an overall this. The moment we have this equation, we call this as the second order transfer function, because the highest power of s is s square. It is also possible to have only first order, right? Then I have x of s by f of s could be 1 by k1s plus k2. But normally what we do is we write this as uh, k k divided by k divided by s plus tau. where tau we call it as a time constant. We can look at this little later, right? So the moment I get the transfer function, then I can really analyze, right, my uh, behavior of the transducer, right? Of course, here I chose one mass, one damper, and one spring, but in general, a transfer function GFS can be numerator function in S by denominator function in S. So this could be S power n plus kn S power n, kn minus 1 by S power n minus 1 dot dot dot. Similarly, I can have km S power m plus km minus 1 S power m minus 1 dot 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 and k naught. K naught numerator, k naught denominator. It's a general function, right? Uh, Now we can arrange in general this function as numerator as some constant k into s plus or minus zn, right, into s into plus or minus zn minus 1 into, right, like that. Similarly, I can write the denominator as s plus pn plus or minus, it could be minus also. I'll have to put small s plus small s plus or minus pn minus 1 dot 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 s plus or minus p1, right? I wrote it in this particular form because we know Zn when s is equal to minus of Zn, right? If it is s plus Zn, then s is equal to minus Zn. This will go to 0, numerator will go to 0. Then we call this 0. So each Zn, Zn minus 1, Zn minus 2, etc. all zeros, right? Because at those values of s, the transfer function reduces to 0. Similarly, if I look at when s is equal to the Pn matches Pn, negative of Pn, uh, then also I get the value goes to infinity. We call these as poles, right? So a transfer function, depending upon the numerator and the denominator, we have zeros and poles. Okay. Okay. Once I have the transfer function, I can get anything. Let's take an example. Let me say I have g of s is 9 divided by s square plus 4s plus 9, right? So now I have the transducer which has this transfer function. Now, is it possible for me to get the frequency response? Absolutely. All I have to do is to get frequency response, I substitute s is equal to minus j omega, right? If I put s is equal to minus j omega, okay, I can put plus j omega, it doesn't matter, it need not be negative frequency, it can be positive frequency. I put s is equal to j omega or minus j omega, you can decide. We put s is equal to j omega, then this becomes 9 divided by s square is j square omega square, that is minus omega square plus j4 omega plus 9, right? So this is g of j omega, right? I can also put j of minus j omega, it's not a big problem. we can, but using positive quantities has certain ease of handling it. So we will always use S is equal to plus j omega, right? So now I can find out the frequency response by simply taking the magnitude and the phase, right? So if I look at the magnitude of g of j omega, this is 9 divided by square root of 9 minus omega square whole square plus 16 omega square, right? I can rearrange this and get the value. So then I can actually plot this with respect to omega. I will see that I am going to get something like this, right? This is omega, this is magnitude of g of j omega, right here. So we see that it's a low pass function. We can also get the phase response. Phase of omega, phi of omega of the g of j omega, we can calculate it as minus tan inverse 4 omega, this is 16 omega square divided by 4 omega divided by 9 minus omega square. Okay. So for every omega, I can again calculate what would be the phase response of the transducer, right? So the it is also possible, if I have a particular input to this transducer, I can get the Laplace transform of the input, multiply with the G of S and get the L inverse, and I'll get the actual value that I will get for that particular input, right? Now the the moment we keep the transfer function, the moment we obtain the transfer function of a transducer, right? Immediately we can do a lot of things. We can look at how the transducer is going to behave for a particular setup, right? Let me look at a simple, right? This thing, I have input which is AC or DC, it doesn't matter. I have the equivalent circuit of a transducer, right? For example, if I model my mercury thermometer, I will get an equivalent circuit, something like this. This is my input temperature. I have the R thermometer and C thermometer. So if I can write the equation whichever way I want, because it's such a simple one. I can simply write, if I have the input here, I call this as EI of t, and this is E naught of t. I can write E naught of t, E naught of s. Let me not go there. This we have already seen. The value of this would be 1 by SC, and this is simply R, right? If I do that, then I can calculate E naught of S equal to E I of S into 1 by 1 plus S tau, where tau equal to R into C, the time constant of the circuit, right? So we can take this particular uh, example, and now I see that it has only S power 1. So we call this as first order transfer function, or simply a first order system. The first order system has only a resistor and a capacitor, or resistor and inductor. It doesn't matter what we can use. Nicely, there is no problem, right? And if I have the input to the system, I can calculate the output, right? So if I look at this 1 by s plus tau, I know I am going to get the inverse Laplace transform would be 1 minus e power minus 1 by tau will be the, right. So if I put this with respect to time, right, I will get something like this. So we call this as the first order transfer function. So we again have transient phase here, and we have steady state phase here, right? I am going a little fast because I assume that all of you know this. If you really want me to revisit this, uh, you can send me an email. I will revisit this, because this you would have done in several subjects in your UG, right? The transient response of a first order system, transient response of a second order system. Only thing is, now we are looking at it as the response of different types of transducers, right? As I already said, the mercury thermometer will fit exactly into a first order system, so it will have only one delay at time constant, right? And if I have the second order transfer function, this we have already put uh, x of s by f of s equal to 1 by m s square plus ds plus ks, right? Now what I do is I divide both numerator and denominator by m, so this is 1 by m, right? And I am going to get s square plus d by m into s plus ks by m, right? Okay. Now what I do is I am going to rewrite this into a standard format, s square plus 2 alpha omega n plus omega n square, right? So the numerator would be 1 by m. Okay. Uh, Now I look at this equation and this equation. I have just rewritten this in that format. I immediately know omega n is equal to royal square root of ks by m, right? We call this as the natural frequency of the system. And if I now equate uh, d by m is equal to 2 alpha, one s is missing, omega n, then I can calculate uh, the value of alpha, right? Uh, Quite easy, right? I am not doing this for obvious reasons. Please calculate what should be the value of alpha in terms of D, M, and Ks, right? That's the one. Okay. So why did I do this? Because now I know this is second order equation, and it depends on the value of xi, right? If I look at this, will have two roots, root 1 and root 2. Root 1, I call this as minus alpha plus square root of alpha square minus 1, and the root 2 would be wait a minute, minus I plus square root of into omega n. That will be one root. The other root would be minus alpha minus square root of alpha square minus 1 into omega n, right? Now if I look at if I look at alpha equal to 1, right? When alpha equal to 1, what happens? Alpha square minus 1 becomes 0. Alpha square minus 1 becomes 0. So alpha is anyway 1. So I'll have minus 1 omega n. So this is minus omega n. This is also minus omega n. Right? So if I look at this, if alpha equal to 1, then I get two roots exactly at the same value, omega n and omega n, right? If alpha is greater than 1, then this would be some root 1, this would be some root 2. Of course, I will get both real roots. So I get real roots. When alpha is less than 1, both will be complex roots, right? This will be complex. This will also be complex roots, right? So we can now look at these roots and get back the response, right? So and we can write this very nicely. If I give input as u of t, right? So u of s would be 1 by s. I have to multiply this by s and find the solution. There would be three possible scenarios. For alpha greater than 1, I will get two exponentials. I am not again doing this because you would have done this in the control system, right? And if I put alpha equal to 1, I will get something like this. This is alpha equal to 1. If I get alpha less than 1, then I may get something like this. So we have overshoot and undershoot. So this is alpha less than 1. So the transducer response depends on this particular value alpha, which is called the damping constant, right? The damping constant, as far as possible, should be nearer to 1, right? When you design, okay, we can have the different types of models for a given transducer. As I said, when we look at our real transducers, all these will become clear because we are going to apply this there, right? Um, so it's possible that I can get uh, the model of a transducer either as electrical equivalent circuit or in terms of transfer function, right? Uh, we can analyze it as we wish. These are the tools that we actually learned in our earlier courses that we will be using here to analyze our transducer. Now, these are internal characteristics that tell us about the response of a transducer for a given input, right? So if I apply a particular input, whether it's a DC input or AC input, what will happen to the output, how the transducer will behave, uh, all these parameters. Now there is also another set of characteristics for the transducer that depends upon the operating environment. Okay. Uh, for example, a transducer uh, can work only within the range of temperature, right? So environment, we have temperature, right? So the transducer can work only up to 0 degrees to 50 degrees centigrade, otherwise it won't work. Or sometimes we really need a transducer that will work up to 600 degrees centigrade. Okay, so these thus the temperature of the environment in which the transducer work becomes an important parameter. So you should carefully look at before using a transducer whether it will operate at that particular temperature you want the transducer to operate. Okay. The second part of the transducer, the when I talk about environment, the second parameter is humidity, right? So this is water vapor in the atmosphere. So for example, if you are in a desert, there will be absolutely no water vapor in the atmosphere, especially during the noon hours. So it's completely dry and hot. On the other hand, if you are in a seashore, the air is soaked full of water vapor, so we may have 100% humidity or 95%, 96% humidity, right? uh, then it's also possible that the transducer may have to handle certain amount of water itself, right? Maybe I am going to use it in a place where there will be water spray, right? I should be able to, apart from the humidity, we also have to look from look for the, so in the temperature we can say there are two things: storage temperature, operating temperature. So maybe storage temperature is minus 30 degrees centigrade to 50 degrees centigrade. Operating temperature is 0 degrees centigrade to 50 degrees centigrade. So I am giving a very typical value. It varies from transducer to transducer, and again humidity uh, up to 95%. So humidity, the specification could be less than 95%, and sometimes they also use and non-condensing. Do you understand what non-condensing means? I can tolerate humidity, but it should not convert itself into water molecules, right? Water particles can be in the air, but it cannot become a dew on the transducer. Then the transducer will not work, right? Uh, then apart from these two, uh, there is another part of the transducer, uh, another environment that the transducer may be put to. For example, it could be that we have the transducer comes into contact with foreign material, right? Especially dust, right? Or sometimes even bigger particles can come into contact with the transducer, and how will the transducer protect, right? Will work. So this particular characteristics is called ingress protection, right? And so these characteristics are all in standards. The American standard AS 1939. This is not 1939, 1939. That's a number. It's not a year. And International Electrical Commission IEC Electrical Commission 529, and European Normung EN 60529. These are the ones that describe uh, the conditions in which the transducer can work, right? Uh, so the in the past, the IP class of the transducer was given as IP ingress protection K, L, M, uh, X and Y, right? So okay, um, so here K is protection against, or ability to work against, contact with objects, right? And the value can go through uh, 0 to 7, right? 0 to 6. 0 to 6. 0 means you cannot make the transducer work. It's very flimsy. It cannot come under. 1 means it can come into contact with bigger particles, 50 millimeter in diameter, and it will still withstand and work. 2 would be 12.5 millimeter particles, and 3 would be 2.5 millimeter particles. 4 would be 1 millimeter particle, and 5 will be dust proof, right? So which means it can work under dusty environment. If it is 6, it simply says the transducer will work in any kind of environment, right? You don't have to really worry about it. Similarly, the other uh, number L, that transfers to in terms of ingress of water, right? So if it is 0, of course, it will not work if water is poured on the transducer. It will simply fail. If it is 1, of course, it can work up to certain amount of water on it. If it is 2, it will work even if the water is comes at an angle and higher amount of water, right? And this number as keeps increasing, the water level can go. So when KL becomes 7, the water can, the transducers can work even if it is immersed in water. Right? So many times you will see that the transducer is IP67 class. This is normally the best class. There is also 68, but that's very, very rare. 68 is submerged in water at a depth, right? So 67 is up to 1 meter, and sometimes we can go up to 68, which is 30 meters, 100 meters, 200 meters inside the water, right? Depth, at that depth of water, it will still work, right? IP67 simply says that it will work in any dusty environment, right? It doesn't matter, it can handle it. And even if it is submerged in water up to 1 meter, it will work. So many times you will also see manufacturers selling IP67 enclosure. So if you keep anything inside, and that enclosure protects whatever you keep it inside at the in terms of dust and water level, right? Then there is also impact withstanding capability, right? Uh, Earlier it was part of ingress protection class. Now we do not use ingress. Uh, the ability to withstand impact energy is not part of IP class. It has been separated out, and today we have something like called the IK code, right? That tells us um, what is the ability of a transducer to uh, vibration or shock, right? So we call this as IK code. So this is covered, and European norm 62 262. I'll have to check this. I think my memory is okay. So that would be the standard. The This goes from IK00 to 10, IK10, right? So what it means is that it can take certain amount of impact energy, right? So if I put the transducer, this is my transducer, and I drop a weight, right, on it, okay, uh, whether it will handle that, whether it will continue to work after the object hits, that is given by the IK code. For example, IK10, uh, if a transducer has the IK10, then what it means is I can put the transducer, I can lift 5 kilograms to 40 centimeters height and drop it on the transducer, right? That 5 kg mass just goes on the transducer dome, and nothing will happen to the transducer. The transducer can withstand, right? So if I calculate the amount of energy that is impacted when the 5 kg falls from a height of 40 centimeters on the transducer, is roughly about 20 kilojoules, right? It can withstand. There is one more uh, vibration and shock. Of course, you vibrate, you simply shake the transducer to certain level. It will still work. Vibration is given in terms of G, where G is uh, gravity, right? Acceleration due to gravity, uh, approximately 10 meter per second square, right? So if the transducer manufacturer says my transducer will take 2G vibration, so you can actually vibrate with respect to that kind of acceleration in your vibration, it will still not work. G vibration is acceleration, which is d square x by dt square. Shock is d cube x by dt cube, right? So, for example, if I throw the transducer on the wall, the transducer picks up velocity, acceleration, and when it hits a wall, suddenly all the dynamics come to zero. It hits a wall and falls down. So that is shock. So shock is also uh, put in terms of G, right? Actually, it is G per second. Uh, but these are rare qualities of a transducer you will be looking for. Generally not for a commercial type of transducer. When you want to use a transducer for special purposes, for example, it could be military purposes, we use all these IP, IK, vibration, shock, and so on. So I stop here. I'll continue in next week. Okay.